Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a strange and beautiful question about light, time, and the age of the universe itself. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. Tonight we'll explore a curious idea that emerges from Einstein's theory of relativity. According to modern physics, light travels at the fastest speed anything in the universe can move. It races through the cosmos at about 300,000 kilometers per second, fast enough to circle the Earth more than 7 times in a single second. And yet, hidden inside this familiar number is a very strange implication. For objects that move close to this ultimate cosmic speed, time begins to behave differently. Clocks tick more slowly, moments stretch and bend. The faster something moves, the more its experience of time begins to change. And if something could travel exactly at the speed of a light, something like a photon, the tiny particle of light itself, then the equations of relativity suggest something remarkable. Time, along that path, does not pass at all. From the photon's journey through space-time, the moment it leaves a distant star and the moment it drives somewhere else may be connected by what is effectively the same instant. If that idea feels a little strange, that is perfectly normal. It puzzled physicists for decades, and it continues to inspire both curiosity and philosophical reflection today. Because if light does not experience time, then some of the oldest light in the universe, light that has travelled for nearly 14 billion years, might, in a certain sense, still be in the same moment in which it was created, which leads to an almost poetic question. Could the light released near the beginning of the universe still be experiencing that moment right now? And if so, what does that say about time itself? Is the universe truly evolving through time the way we imagine? Or could it be something more like a vast 4-dimensional landscape, where past, present, and future all quietly coexist? These are the ideas we'll explore together tonight. There is no rush, no equations to solve, just a slow journey through space-time, guided by the soft glow of physics and the quiet curiosity that has always driven humans to look up at the stars. And we'll begin somewhere very simple, with a single ray of light. Now imagine something simple. Perhaps you are sitting near a window during the daytime. Sunlight slips through the glass and lands softly on your hand. It feels warm, gentle, almost weightless. That warmth began its journey far away, inside the heart of the sun. Deep within our star, powerful reactions release enormous amounts of energy. Some of that energy escapes in the form of tiny packets of light called photons. These photons then begin a long outward journey through space. From the surface of the sun to the Earth is about 150 million kilometers. That sounds like an enormous distance. And even moving at the fastest speed allowed by nature, about 300,000 kilometers every second, it still takes light around 8 minutes to reach us. So the sunlight touching your hand right now actually left the sun about 8 minutes ago. If the sun were to suddenly vanish, the Earth would continue to receive sunlight for those same 8 minutes before darkness arrived. In everyday life, we imagine this journey very clearly. We picture light travelling through space second by second, crossing the gap between star and planet like a tiny messenger racing across the cosmic ocean. And from our perspective here on Earth, that picture is exactly right. We measure the passage of time with clocks. We see the light leave the sun, we see it arrive here. Between those two events lies a span of about 8 minutes, but physics sometimes invites us to ask a slightly different question. What would that journey look like from the point of view of the light itself? This is where the story becomes surprisingly strange. In Einstein's theory of relativity, space and time are not separate things. They form a single woven structure called spacetime. Every object in the universe moves through this structure in its own way. Slow-moving objects like people, planets, or drifting clouds move mostly through time. Seconds pass, normally for us. Our clocks tick forward at a steady pace, but as an object begins to move faster through space, something subtle begins to happen. Its motion through time slows down. This effect has been measured many times in real experiments. Clocks carried on fast airplanes tick slightly more slowly than clocks on the ground. Satellites orbiting Earth experience tiny shifts in time that engineers must carefully correct when running the global positioning system. The faster something moves, the more time itself begins to stretch, and as motion approaches the ultimate cosmic speed, the speed of light, this stretching becomes more and more dramatic. Clocks would tick slower and slower. Moments would become longer and longer, until at the exact speed of light, the mathematics of relativity tells us that time along that path becomes zero. This does not mean time stops everywhere in the universe. It simply means that along the path taken by a photon, the amount of time experienced between two events becomes nothing at all. In other words, if a photon leaves the surface of the sun and eventually reaches your eye, the equations describing that journey connect those two events without any passage of time along the photon's own path. From our perspective, 8 minutes pass. From the geometry of the photon's path through space-time, the emission and the arrival are connected in what behaves like a single instant. It is important to understand that photons do not have thoughts or experiences. They do not perceive time stopping. In fact, relativity does not allow us to assign a true frame of reference to light itself. But the mathematics describing space-time still reveals something remarkable. The path taken by light is fundamentally different from the paths taken by objects with mass. For ordinary objects, time always moves forward. For light, time does not accumulate at all, and this strange property of light leads to one of the most intriguing consequences in modern cosmology. Because the universe is filled with ancient light, light from distant galaxies, light from exploding stars, light from the earlier stages of the universe itself. Some of those photons have travelled across space for nearly 14 billion years before reaching our telescopes. Yet along the path of those photons, the passage of time may be zero, which means that the moment when they were born and the moment when they arrive here could be connected by the same timeless thread of space-time. The story of light, it turns out, may also be a story about the nature of time itself. And to understand why this happens, we need to take a closer look at that famous cosmic speed limit, the speed that nothing in the universe can exceed. Because this number is not simply about how fast light moves, it is something much deeper. It is the speed at which cause and effect themselves travel through the fabric of reality. As we continue this quiet journey through space-time, let's linger for a moment on that remarkable number we mentioned earlier, the speed of light. You may have heard it many times before, in textbooks, documentaries, or perhaps during a late-night curiosity about the universe. Someone mentions that light travels at about 300,000 kilometers every second. It is such a large number that it almost loses its meaning. Numbers that big often float past our imagination without leaving much of an impression. But physicists do not think of this number as simply the speed of light. They think of it as something far more fundamental. In the language of physics, this speed represents the maximum rate at which information can travel through the universe. It is the fastest speed at which any cause can influence an effect somewhere else. In other words, it is the speed at which the universe allows events to communicate with one another. Imagine you turn on a flashlight in a dark room. The beam spreads outward almost instantly to your eyes, illuminating the space around you. But even that beam, incredibly fast as it is, still follows this universal speed limit. Nothing, not a particle, not a signal, not even gravity itself, can carry information faster than this cosmic speed. To understand why that matters, it helps to think about how events influence one another. Suppose a star explodes somewhere far away in the galaxy. The explosion sends out light and other signals in every direction. Those signals carry information about the explosion, its brightness, its energy, its violent release of matter. But that information cannot spread infinitely fast. Instead, it expands outward at a fixed speed, like ripples spreading across the surface of a calm pond after a stone has been dropped. The ripples carry the news of the splash outward, and the speed of those ripples in the universe is always the same, 300,000 kilometers per second. This limit creates a kind of structure for reality itself. Events can influence nearby places quickly, but distant places must wait longer for the message to arrive. Light from the moon takes about 1 second to reach Earth. Light from the sun takes around 8 minutes. Light from the nearest star system beyond our sun takes more than 4 years. And light from the most distant galaxies we observe has been travelling for billions of years before finally reaching our telescopes. The universe, in this sense, is not just a collection of objects scattered in space. It is a network of events connected by signals that travel at a fixed cosmic speed. Physicists sometimes describe this using a simple idea called a light cone. You can imagine it like this. Picture an event happening right now, perhaps the moment a photon leaves the surface of a star. From that moment, signals begin travelling outward in every direction. If we could draw the possible paths those signals might take through space-time, they would form a widening shape, like the beam of a flashlight spreading outward through darkness. Only events inside that expanding region can be influenced by the original event. Anything outside that region cannot yet know that the event occurred. This structure divides space-time into regions of cause and effect. Some events can influence each other, others remain forever disconnected. The speed of light defines the boundary between those possibilities, and this is why physicists sometimes say that the speed of light is really the speed of causality. It is not simply the speed of photons racing through space, it is the speed at which the universe allows information to travel. Now here is where things become even more interesting. If this speed is truly the same everywhere in the universe, if it does not change depending on how fast you are moving, then space and time themselves must adjust in order to keep that rule true. That realization was one of the most revolutionary insights of Einstein's theory of relativity. Before Einstein, many scientists imagined that space and time were fixed backgrounds, like a stage on which the drama of the universe played out. Space was simply the distance between things. Time was simply the ticking of a universal cosmic clock. But Einstein discovered that this picture could not be correct if the speed of light is always the same for every observer. Imagine 2 observers watching the same beam of light. One observer is standing still, the other is racing past at incredible speed in a spacecraft. In everyday life, we would expect them to measure different speeds for the moving beam of light. After all, if you chase a car down a highway, its speed relative to you appears smaller than it does to someone standing on the roadside. But light does not behave this way. Both observers, no matter how fast they move, will measure exactly the same speed for the beam of light. To make this possible, the universe performs a subtle adjustment. Distances, can change, time can stretch. The measurements of space and time shift just enough to preserve that cosmic speed limit. In other words, the universe protects the speed of light by allowing space and time themselves to become flexible. This flexibility leads directly to the phenomenon we touched on earlier, time dilation. Objects moving very fast through space experience time more slowly, compared with objects that remain relatively still. This is not just an abstract theory. It has been confirmed in laboratories and in everyday technology. Atomic clocks flown around the Earth in aircraft show measurable differences in time compared with clocks left on the ground. Satellites orbiting our planet must account for these effects to keep navigation systems accurate. Even astronauts aboard the International Space Station age slightly more slowly than people on Earth, though the difference is tiny, amounting to only fractions of a second. These effects become dramatic only when speeds approach the cosmic limit. As motion through space increases, motion through time decreases, and this trade-off leads us back to the strange case of light itself. Because photons move at the very speed that defines this cosmic limit, they move through space as fast as the structure of space-time allows, and when something moves at that speed, the mathematics of relativity shows that its journey through time becomes zero. Which means the strange behaviour of light, the timeless path connecting distant events, is not an accident. It is a direct consequence of the universe's most fundamental rule. Nothing can carry information faster than the speed of light. And to enforce that rule, space-time itself bends, stretches, and reshapes the flow of time. Soon we will explore what this means in more detail. Because when time slows and space begins to shrink at extreme speeds, something truly remarkable happens. Distances that appear enormous to us can become astonishingly small, and the universe begins to look very different depending on how fast you move through it. One of the most beautiful insights in modern physics is also one of the simplest to imagine once we approach it gently. Space and time are not separate things. Instead, they form a single structure, something physicists call spacetime. This idea may sound abstract at first, but a simple picture can help. Imagine the universe as a vast landscape, not just of space, but of both space and time woven together. Every event, every star being born, every planet forming, every beam of light crossing the sky exists somewhere within this four-dimensional fabric. In everyday life, we think of space as the three directions we can move: forward and backward, left and right, up and down. Time feels different. It seems like something that simply flows, carrying us from the past toward the future. But relativity suggests that space and time are not truly independent. They behave more like two parts of the same woven cloth. If you pull gently on one thread, the others shift as well. To understand this connection, imagine something simple. Picture yourself sitting quietly in a chair. You may feel completely still. Nothing about your body seems to be moving. Yet even in this moment of stillness, you are travelling through space-time. The Earth rotates beneath you. The planet orbits the Sun. The Sun moves through the galaxy. The galaxy itself drifts through the vast cosmic web of the universe. So even while sitting quietly, you're actually moving through space at tremendous speed. But relativity tells us something even more surprising. Every object in the universe is always moving through space-time at a constant overall rate. Not just through space, but through the combined structure of space and time. You can imagine it a little like walking along a path. You may choose to walk more toward the east or more toward the north, but your total walking speed along the path remains the same. In a similar way, motion through space-time can be shared between movement through space and movement through time. If you move very slowly through space, like a person sitting in a chair, almost all of your motion through space-time happens in the direction we call time. Your clock ticks normally. seconds pass at the familiar pace we experience every day. But as something begins to move faster through space, some of that motion shifts away from the time direction. The object still moves through space-time at the same overall rate, but a larger portion of that motion is now spent travelling through space. The result is subtle but profound. Less motion remains for the direction of time, which means time itself begins to pass more slowly for that moving object. This idea might sound mysterious, but it has been tested many times. Physicists have carried extremely precise clocks on airplanes travelling around the Earth. When those clocks returned and were compared with identical clocks that remained on the ground, the travelling clocks were found to be slightly behind. The difference was tiny, only fractions of a second, but it was exactly what relativity predicted. The clocks moving through space had experienced a slightly slower passage of time. This effect becomes stronger as speeds increase. At the speeds of everyday vehicles, cars, trains, even aircraft, the difference is almost impossible to notice. But when speeds approach the scale of satellites orbiting Earth, the effect becomes measurable. And when speeds approach the speed of light, the effect becomes dramatic. To help picture this, imagine a traveller embarking on a long journey in a spacecraft. As the spacecraft accelerates faster and faster, approaching the cosmic speed limit, the traveller's motion through space-time begins shifting more and more toward the spatial direction. Less and less motion remains in the direction of time. For the traveller, clocks tick more slowly compared with clocks on Earth. Days pass normally for the traveller, but far more time may pass for people watching from afar. This is why physicists sometimes describe motion through space-time as a kind of balance. The faster you move through space, the slower you move through time. The slower you move through space, the faster you move through time. Both kinds of motion are part of the same deeper journey through space-time itself. And this balance becomes especially important when we consider the ultimate limit: the speed of light. Photons, tiny particles of light, always move at this maximum cosmic speed. They do not accelerate toward it. They are simply born moving at that speed and continue moving that way until they interact with something else. Because they travel at the fastest speed allowed by the structure of space-time, their motion through space-time is directed entirely through space. No motion remains in the time direction. And this is why the equations of relativity tell us that the passage of time along the path of light is zero. Again, it is important to understand what this does and does not mean. Photons do not experience consciousness. They do not observe time stopping. Physics does not assign a viewpoint to light itself. But the geometry of space-time still reveals something remarkable. If a photon leaves a distant star and travels across the galaxy, before eventually being absorbed by a telescope on Earth, the entire journey lies along a path where the passage of time is effectively zero. From our perspective, millions or even billions of years may have passed, but along the photon's path through space-time, the beginning and the end of that journey remain connected without any accumulation of time. This strange property of light is not merely a curiosity. It plays a central role in how the universe works. Because light carries information between distant places, it links stars to planets, galaxies to observers, and the earliest moments of the universe to the present day. Every photon that reaches your eye has travelled along one of these special paths through space-time, a path where time, in a very real sense, does not pass. And this leads to another remarkable consequence of relativity. As motion through space increases and time slows down, distances themselves also begin to change. Space, like time, becomes flexible. And when speeds approach the speed of light, the universe can begin to appear much smaller than we normally imagine. Now that we've gently introduced the idea of space-time and the balance between motion through space and motion through time, it helps to explore what this actually looks like in practice. Physicists often use thought experiments, simple, imagined scenarios, to reveal how the universe behaves under unusual conditions. One of the most famous examples involves nothing more complicated than two clocks. Imagine placing one clock on Earth. It sits quietly on a table, ticking steadily, measuring thus passing seconds. Now imagine placing another identical clock aboard a spacecraft. At first, the spacecraft is still on the ground, and both clocks tick in perfect synchrony. Every second that passes for the clock on Earth also passes for the clock on the spacecraft. But then the spacecraft begins to accelerate. It rises into the sky and continues to move faster and faster, eventually travelling at incredible speed through space. From the point of view of the astronaut inside the spacecraft, nothing unusual happens. The clock beside them continues to tick normally. Seconds pass just as they always have. Their heartbeat remains steady. Their thoughts unfold at their usual pace. But observers on Earth, watching the spacecraft race across the sky, would notice something remarkable. The clock on the spacecraft begins to tick more slowly. Not dramatically at first. At everyday speeds, the effect is far too small to notice. But as the spacecraft approaches extremely high velocity, the difference becomes measurable. Every second experienced by the astronaut corresponds to slightly more time passing for observers on Earth. In other words, time for the moving traveller begins to stretch. Physicists describe this effect using a relationship that connects speed with the passage of time. Rather than focusing on the equation itself, it is easier to think about what the relationship means. The closer an object's speed gets to the cosmic limit, the speed of light, the slower time moves for that object compared with a stationary observer. If a spacecraft were travelling at about 90% of the speed of light, time for the traveller would pass noticeably more slowly than time on Earth. If the spacecraft reached 99% of the speed of light, the effect would become even more dramatic. A journey that might appear to take many years from Earth perspective could feel much shorter to the traveller, and if an object could somehow move at the speed of light itself, the mathematics of relativity suggests that time along that path would not pass at all. The clock would not tick, moments would not accumulate, the entire journey from beginning to end would be connected by a single timeless path. This idea may sound almost like science fiction, but the slowing of time for moving objects is not merely theoretical. It has been tested repeatedly in the real world. One famous experiment took place in the early 1970s. Physicists placed extremely precise atomic clocks on commercial airplanes and flew them around the Earth. After the flights were complete, the clocks from the airplanes were compared with identical clocks that had remained on the ground. The result matched Einstein's predictions perfectly. The clocks that had been moving through the air showed slightly less elapsed time than the clocks that had stayed on Earth. The difference was tiny, only billionths of a second, but it was measurable and consistent. This confirmed that motion through space really does affect the passage of time. The same principle operates in modern technology. Satellites that orbit Earth are constantly moving at very high speed relative to the surface of the planet. Because of this motion, the clocks aboard those satellites tick at a slightly different rate compared with clocks on the ground. If engineers ignored this effect, navigation systems like GPS would quickly accumulate errors of several kilometers. To keep the system accurate, the satellite clocks must be adjusted using the predictions of relativity. So the strange idea that time slows down for moving objects is not just an abstract theory. It is something our everyday technology depends on. But there is an even deeper implication hidden inside this phenomenon. Imagine a traveller leaving Earth in a spacecraft capable of reaching extremely high speeds. Suppose this traveller accelerates until their ship moves at 99% of the speed of light. From the traveller's perspective, time continues normally. Their clock ticks as usual, Their life unfolds second by second. But from the perspective of observers back on Earth, the traveller's clock appears to run slowly. Years on Earth might pass while only a small amount of time passes for the traveller. If the traveller later returns to Earth, they may find that many more years have passed for the people who remained behind. This situation is sometimes called the twin paradox. One twin stays on Earth. The other twin travels through space at tremendous speed. When the traveller returns, they are younger than their sibling, not because of magic or science fiction, but because their journey through space-time followed a different path. Relativity shows us that time is not universal. It does not flow at exactly the same rate for everyone. Instead, time is woven into space-time itself, and different paths through that fabric lead to different experiences of time. For objects with mass, time always moves forward, though its rate can change depending on motion and gravity. But light behaves differently. Photons do not slow down or speed up. They always travel at the same cosmic speed. Because of this, their path through space-time lies entirely along the direction of motion through space. No portion of their journey remains for motion through time, which means that along the path taken by light, time does not accumulate. The emission of a photon and its eventual absorption are linked by a path where the passage of time is zero. To us, watching from our slower journey through space-time, that path may stretch across millions or billions of years. But the geometry of space-time quietly connects those distant events along a single timeless thread. And once we begin to understand this strange relationship between motion, time, and light, another surprising consequence begins to emerge. Because time is not the only thing that changes at high speeds, space itself begins to behave differently as, well, distances can shrink, paths can shorten, and from the perspective of something moving close to the speed of light, the universe itself can appear far smaller than we normally imagine. As we continue drifting through these ideas, it may help to imagine a journey that pushes closer and closer to the ultimate speed allowed by nature. Earlier we spoke about a spacecraft carrying a clock. As the spacecraft moved faster through space, the clock on board began to tick more slowly compared with clocks on Earth. At first, the difference was tiny, but what if the spacecraft could keep accelerating? What if its engines continued pushing it faster and faster, closer to the cosmic speed limit, the speed of light? To picture this, imagine a series of travellers leaving Earth in identical spacecraft, each one moving faster than the last. The first traveller moves at 10% of the speed of light. That is already incredibly fast, far beyond anything humanity can currently achieve. But even at that speed, the effect on time would still be extremely small. The traveller's clock would tick just slightly more slowly than clocks on Earth. The second traveller moves faster, perhaps at half the speed of light. Now the difference begins to grow more noticeable. Time on the spacecraft passes a little more slowly compared with time for observers on Earth. Days on the spacecraft correspond to slightly longer periods on Earth. The third traveller moves even faster, perhaps 90% of the speed of light. Now relativity begins to reveal its strange nature. At 90% of light speed, time on the spacecraft slows dramatically relative to Earth. For every 10 years that pass on Earth, the traveller might experience only about 4 years. Their journey through space-time is tilted heavily toward motion through space, leaving less motion available for the passage of time. And if the spacecraft could accelerate even further to 99% of the speed of light, the difference becomes even more dramatic. Years for the traveller could correspond to decades for observers on Earth. At 99.9% of the speed of light, the gap becomes enormous. A traveller might cross vast stretches of the galaxy while aging only a few years, even though thousands of years might pass for distant observers. This effect arises from the same relationship we discussed earlier. The faster something moves through space, the slower it moves through time. Physicists sometimes describe this relationship using a mathematical expression that connects velocity with the flow of time. Rather than focusing on the equation itself, it helps to remember the meaning behind it. As an object's speed approaches the speed of light, the passage of time for that object stretches further and further compared with slower observers. There is no sudden boundary where the effect begins. Instead, the slowing of time increases smoothly as speed increases, but something special happens at the ultimate limit. If an object could move exactly at the speed of light, the mathematics shows that the passage of time along its path would become zero. In other words, the journey through space-time would contain no progression of moments. This limit cannot be reached by objects that have mass. Every particle with mass, atoms, people, spacecraft, planets, requires more and more energy to move faster. As its speed approaches the speed of light, the energy required to accelerate it further grows enormously. Eventually, the required energy becomes effectively infinite. Nature prevents massive objects from reaching that ultimate speed. But photons, particles of light, are different. They are born moving at the speed of light and always continue at that speed until they interact with matter. Because they already travel at the maximum allowed velocity, their path through space-time lies entirely along the spatial direction. None of their motion remains in the direction we experience as time. Which brings us back to the strange statement that began our journey tonight. Along the path taken by light, time does not pass. Consider a photon created in the fiery atmosphere of a distant star. That photon might travel across space for millions of years before reaching a telescope on Earth. Astronomers measure that journey as a vast stretch of time, yet the geometry of space-time connects the beginning and end of that journey along a path where the accumulation of time is zero. The photon's emission and its arrival lie on the same timeless thread. This idea is subtle, and it can be easy to misunderstand. It does not mean that the photon somehow experiences the universe instantly, nor that time truly stops everywhere. Instead, it means that the structure of space-time itself allows certain paths, those followed by light, to connect events without the passage of time along that path. The universe contains many such paths. Every beam of light travelling between two events follows one of them. When a star shines, when a supernova explodes, when sunlight reaches your eyes, photons are tracing these special routes through space-time. These routes form the network through which information moves across the cosmos. And because light always travels at the same cosmic speed, these paths define the ultimate structure of cause and effect in the universe. They determine which events can influence one another and which remain forever beyond each other's reach. But the strange behaviour of light at high speeds reveals another consequence of relativity that is just as surprising. When objects move close to the speed of light, time slows, but space itself begins to change as well. Distances that appear enormous to stationary observers begin to shrink for travellers moving at extreme speeds. From their perspective, the universe becomes shorter along the direction of motion. Paths that once stretched across vast regions of space begin to contract. This effect, known as length contraction, works together with time dilation to preserve the same cosmic speed limit for everyone. And when we combine these two effects, time slowing and space shrinking, the universe begins to look very different depending on how fast you move through it. For travellers approaching the speed of light, distant destinations may appear far closer than they do to observers who remain still. The vastness of the cosmos itself begins to compress. And when we follow this idea to its ultimate limit, something truly astonishing emerges. From the path followed by light itself, the distances between events can collapse to zero, which means that for light, not only time but distance itself can disappear along the direction of its journey, And that realization leads us to one of the most mind-bending implications of relativity. Because if time can vanish, and distance can shrink to nothing along the path of light, then the universe may look profoundly different from the perspective of something travelling at that ultimate cosmic speed. As we drift deeper into the strange territory revealed by relativity, we arrive at the very edge of motion in our universe, the speed of light itself. Every object we've talked about so far, spacecraft, airplanes, satellites, even the fastest particles created in laboratories, move slower than this ultimate limit. They may come close, they may approach it with astonishing speed, but they never quite reach it. There is always a small difference between their velocity and the cosmic speed limit. Light, however, is different. Photons do not gradually accelerate toward the speed of light. They do not slowly climb up to it. They begin their existence already moving at that speed. From the moment a photon is created, perhaps deep inside a star or during a burst of energy in a distant galaxy, it immediately travels through the universe at about 300,000 kilometers every second. It never slows down while traveling through empty space. And because of that, photons follow a very special kind of path through space-time. To understand why this matters, it helps to return to the balance we discussed earlier. The idea that every object moves through space-time in a way that combines motion through space and motion through time. For slow-moving objects like people or planets, most of that motion points in the direction we call time. Our clocks tick normally, our lives unfold moment by moment. But as objects move faster through space, their path through space-time tilts more strongly toward the spatial direction. Less motion remains in the time direction. This is why time slows for fast-moving travellers. Now imagine pushing this idea all the way to the extreme. Imagine a path through space-time that is directed entirely along the spatial direction. No portion of that motion remains pointing toward the direction of time. According to the geometry of relativity, that path corresponds exactly to the motion of light, and along such a path, the amount of time measured between the starting event and the ending event becomes zero. In physics, we sometimes say that the proper time along the path of light is zero, but rather than focusing on technical terms, it may be easier to think of it this way. For objects with mass, a journey through space-time always accumulates moments. Seconds pass, clocks tick, memories form. For light, the path between two events contains no accumulation of moments at all. The beginning and end of the journey lie on the same timeless connection. To illustrate this idea, imagine a photon leaving the surface of the Sun. The Sun sits about 150 million kilometers away from Earth. From our perspective, the photon spends 8 minutes travelling across space before reaching our planet. Astronomers measure that journey easily. We can calculate it precisely, but the geometry of space-time tells a different story along the path followed by the photon itself. Along that path, the moment of emission and the moment of arrival are connected without the passage of time. It is as if the two events lie along a single thread in space-time, tied together without any stretch of time between them. Again, it is important to keep the interpretation careful. Photons do not experience time in the way living beings do. They do not observe their journey. Relativity does not assign a meaningful viewpoint to an object travelling exactly at the speed of light. But the mathematics describing space-time still reveals something profound about how the universe is structured. Light moves along special pathways, routes through space-time where time itself does not accumulate. These pathways are sometimes described as the edges of causality. They mark the boundary between events that can influence each other and events that cannot. Whenever one event sends a signal to another event using light, the connection between them lies along one of these special paths. A star explodes in a distant galaxy. a photon travels across the darkness of space. Billions of years later, that photon enters a telescope on Earth. To us, those two events are separated by immense stretches of time and space. But the path of the photon quietly connects them along a single line through spacetime. This strange property of light becomes even more remarkable when we think about the scale of the universe itself. Because some of the light we detect today began its journey near the earliest moments of cosmic history. Astronomers regularly observe galaxies whose light has been travelling toward us for more than 10 billion years. Even more ancient light exists. Radiation left over from the early universe itself. These photons have crossed the expanding cosmos for nearly 14 billion years before finally reaching our detectors. Yet along their paths through space-time, the accumulation of time may still be zero. The moment they were created and the moment we detect them today are joined by the same timeless connection. This does not mean that the universe itself is timeless. For objects with mass, planets, stars, people, time continues to move forward. But light reveals something deeper about the geometry of reality. It shows that space-time contains special roots where the separation between events contains no duration at all. And once we begin to understand this idea, another surprising consequence of relativity begins to appear. Because when motion approaches the speed of light, not only does time slow down, but space itself begins to change. Distances begin to shrink along the direction of motion. The faster something travels, the shorter the path ahead appears, and when we imagine pushing this effect all the way to the limit of light itself, the universe begins to behave in an even more surprising way. Along the path of light, both time and distance can collapse to zero, which means that for light, the vast distances of the cosmos may be connected in ways that challenge our everyday understanding of space and time. As we continue our quiet exploration of relativity, we arrive at another surprising consequence of high-speed motion, one that feels almost as strange as time slowing down. Until now, we've been focusing on time. We imagined clocks ticking more slowly for travellers moving at enormous speeds, and we followed that idea all the way to the limit where light itself travels. But relativity tells us that time is not the only thing that changes when motion becomes extreme. Space changes as well. To see why, it helps to imagine another gentle thought experiment. Picture a long train moving along a straight track. You're standing beside the railway, watching the train pass. From your perspective, the train has a certain length. Perhaps it is 1 kilometre long. You can measure that length easily as it rolls past. Now imagine that the train begins to move faster. At everyday speeds, 30 kilometers per hour, 100 kilometers per hour, its length appears exactly the same. There is no noticeable difference. But if the train could somehow move faster and faster, approaching the speed of light, relativity predicts something remarkable. To you, standing beside the track, the train would begin to appear shorter along the direction it is moving. Its length would compress. The faster it moves, the shorter it becomes from your perspective. This effect is known as length contraction. It does not mean the train itself physically squashes like a collapsing accordion. Inside the train, passengers would not notice anything unusual. Their measuring sticks and their sense of distance would remain perfectly normal. But observers outside the train, watching it rush past at extreme speed, would measure a shorter length than observers riding inside it. In other words, the measurement of distance depends on motion. Just as time can stretch or compress depending on how fast something moves, space can stretch or compress as well. Relativity treats space and time as two aspects of the same underlying fabric, and both can adjust to preserve the same universal speed limit. To make this idea easier to picture, imagine once again a traveller in a spacecraft accelerating toward incredible speeds. At first, the traveller sees the universe much as we do. The moon sits about 400,000 kilometres away. The sun lies about 150 million kilometres away. The nearest star beyond the sun is more than 4 light-years away. But as the spacecraft accelerates closer and closer to the speed of light, the geometry of space-time begins to shift. From the traveller's perspective, the distances in front of the spacecraft begin to shorten. The stars ahead appear closer together. The destination of the journey seems nearer than it would appear to observers who remain behind. Faster the spacecraft travels, the stronger this effect becomes. At extremely high speeds, the distances between stars in the direction of motion can shrink dramatically. A destination that appears impossibly far from Earth may appear much closer from the traveller's perspective. This does not violate the cosmic speed limit. The traveller is not moving faster than light. Instead, space-time itself adjusts so that the path ahead becomes shorter for the traveller moving at extreme speed. This effect works hand in hand with the slowing of time we discussed earlier. Time dilation allows travellers moving very fast to experience less passage of time during a journey. Length contraction allows the distance they must cross to become shorter. Together, these two effects preserve the same fundamental rule of the universe. No object with mass can exceed the speed of light. Yet objects moving close to that speed can experience the universe very differently from observers who remain relatively still. To understand how dramatic this difference can become, imagine a spacecraft capable of reaching 99% of the speed of light. From the perspective of observers on Earth, the spacecraft might need several years to travel to a nearby star system. But for the traveller inside the spacecraft, two things are happening simultaneously. First, time on the spacecraft passes more slowly relative to Earth. Second, the distance to the destination star appears shorter along the direction of travel. These two effects combine to make the journey feel far shorter to the traveller than it appears to observers watching from afar. The traveller still moves below the speed of light, but the structure of space-time reshapes the journey. Relativity does not simply slow clocks, it changes the very measurements of distance and duration themselves. And when we push this idea closer to the extreme limit of motion, the consequences become even more fascinating. Because light travels at the maximum speed allowed by space-time. Photons always move at this ultimate cosmic speed, which means they follow the most extreme version of the path we have been imagining. For objects with mass, motion through space-time is shared between movement through space and movement through time. For light, the entire journey lies along the spatial direction. None of the motion remains for time, and as a result, the two effects we have been exploring, time dilation and length contraction, reach their ultimate limit. Along the path of light, time does not accumulate, and the distance along the path shrinks to zero. From our perspective, light can travel across vast cosmic distances. A photon may cross billions of kilometers or even billions of light years before eventually reaching a detector or an eye. But along the geometry of the photon's path through space-time, the separation between those events contains neither time nor distance. Emission and arrival are joined by a single connection. This does not mean the universe physically collapses to a point. Rather, it reveals something deeper about how space-time is structured. Events that appear far apart in both space and time can be connected by special paths where the usual separation disappears. Light traces those paths. Every beam of starlight, every flash of lightning, every glow from distant galaxies follows one of these remarkable routes through space-time. And once we begin to think about the universe in this way, an even more intriguing question begins to appear, because the universe is filled with extremely ancient light. Some photons began their journeys billions of years ago, near the earliest chapters of cosmic history. They have travelled across the expanding universe ever since. Yet along the path of those photons, the separation between their birth and their arrival may still be zero, which means the oldest light in the universe might still be connected to its origin by the same timeless thread of spacetime. Now that we've seen how motion can slow the passage of time and compress distances, we can begin to combine these two ideas. When time dilation and length contraction work together, something extraordinary becomes possible. Journeys across enormous regions of space may appear much shorter to a traveller moving at extremely high speed than they do to observers who remain behind. To explore this idea, imagine a future spacecraft, one far more advanced than anything humanity has built so far. This spacecraft is capable of accelerating until it reaches a speed very close to the cosmic limit, the speed of light. Not exactly the speed of light, because objects with mass cannot quite reach that ultimate velocity, but close enough that the strange effects of relativity begin to dominate the experience of the journey. Inside the spacecraft sits an astronaut preparing for an ambitious mission. The destination is one of the nearest galaxies beyond our own. Our home galaxy, the Milky Way, contains hundreds of billions of stars, but nearby in the cosmic neighbourhood lies another great island of stars known as the Andromeda Galaxy. From Earth, Andromeda is about 2.5 million light-years away. That distance is almost impossible to imagine. Even travelling at the speed of light, a beam of light leaving Earth today would need 2.5 million years to reach Andromeda. For a human traveller moving at ordinary speeds, such a journey would be completely impossible. But relativity quietly changes the story. Imagine the spacecraft accelerating until it moves at 99.9% of the speed of light. To observers on Earth, the spacecraft is racing across space at unimaginable speed. Yet even at that velocity, the journey to Andromeda would still appear to take more than 2 million years from Earth's perspective. No human civilization could wait that long for a traveller to return. But inside the spacecraft, the story looks very different. First, the astronaut's clock is affected by time dilation. Because the spacecraft is moving so quickly through space, time inside the ship passes far more slowly than time on Earth. The astronaut's heartbeat, breathing and thoughts continue at their normal pace, but compared with clocks back on Earth, their clock runs much more slowly. Years for the astronaut might correspond to tens of thousands of years passing on Earth, but that is only half the story. The second effect, length contraction, changes the perceived distance to the destination. From the astronaut's perspective, the distance between galaxies in the direction of travel becomes dramatically shorter. Instead of appearing 2.5 million light-years away, the Andromeda Galaxy may appear far closer along the path of motion. The faster the spacecraft moves, the more the universe compresses along that direction. In an extreme case, the astronaut might experience the journey to Andromeda as lasting only a few decades. From Earth's perspective, millions of years pass. From the astronaut's perspective, a single lifetime may be enough to cross the vast gulf between galaxies. This possibility is one of the most fascinating consequences of Einstein's relativity. It does not allow faster-than-light travel. The cosmic speed limit remains unbroken. But the structure of space-time reshapes the traveller's experience of distance and time. To an outside observer, the traveller takes millions of years to reach their destination. To the traveller, the journey unfolds along a much shorter path through space-time. In other words, the universe itself becomes smaller along the direction of motion. We can imagine this effect as if space-time gently folds in front of the traveller. The faster the traveller moves, the tighter that folding becomes. Distant galaxies draw nearer. Long stretches of empty space shrink. Paths that once seemed unimaginably long begin to shorten. And this reveals something deeply beautiful about the nature of the universe. distance and duration are not fixed quantities carved into the structure of reality. They depend on the path an object takes through space-time. Different observers moving in different ways can measure different lengths of space and different amounts of time between the same two events. Yet the underlying structure of space-time keeps everything consistent. The cosmic speed limit remains the same for everyone. The laws of physics remain the same for everyone. Relativity does not break the universe. It simply reveals that space and time are more flexible than we once imagined. And once we push this idea all the way to its ultimate limit, we encounter something even stranger. Because the traveller in our thought experiment can only approach the speed of light. They never quite reach it. But photons, the tiny particles of light, do travel at that exact speed, which means that the combined effects we have been discussing reach their most extreme form for light itself. For objects moving very close to the speed of light, time slows dramatically and distances shrink dramatically. For light itself, both of these effects reach their ultimate limit. The passage of time along the path of light becomes zero. And the distance along that path collapses to zero as well. In the geometry of space-time, the starting event and the ending event of a photon's journey lie on the same kind of connection, a path where the usual separation of time and distance disappears. From our perspective, the universe is vast. Galaxies are separated by millions or billions of light years. The age of the universe stretches back nearly 14 billion years. But along the paths traced by photons, these enormous separations can be connected by threads that contain neither time nor distance. Light does not merely travel through the universe, it reveals the deep structure of space-time itself. And when we begin to think about the oldest light in the universe, the faint radiation left over from the earliest moments after the Big Bang, this idea becomes even more astonishing. Because some of that ancient light has been travelling toward us for almost the entire history of the cosmos. And yet along its path through space-time, the beginning and the end of that journey may still be connected by the same timeless thread. As we continue drifting through these ideas, let us pause and imagine something extraordinary. Not a spacecraft this time, and not even a traveller moving close to the speed of light. Instead, imagine following the path of light itself. Throughout this journey, we have spoken about photons, those tiny packets of energy that stream from stars, lamps, lightning, and distant galaxies. Photons move through the universe at the fastest speed nature allows, racing through empty space at about 300,000 kilometers every second. For objects with mass, approaching this speed leads to dramatic changes in the flow of time and the measurement of distance. Clocks slow down, distances shrink, journeys that appear impossibly long from one perspective become shorter from another. But light sits at the very edge of this behaviour. Photons do not merely approach the cosmic speed limit, they live on it. And when we follow the path traced by light through space-time, the strange effects we've been discussing reach their most extreme form. To understand this, imagine two events in the universe. The first event might be the birth of a photon deep inside a distant star. The second event might be the moment that photon enters a telescope here on Earth. From our perspective, those two events may be separated by millions of years and vast stretches of space. Astronomers might calculate that the photon travelled across hundreds of trillions of kilometres before finally reaching us. But relativity reveals that there is a special kind of path connecting these two events. That path is the one followed by light. Along this path, the usual separation between events behaves in a very unusual way. The passage of time along the path is zero. The distance along the path also becomes zero. In the language of space-time geometry, the two events are joined by what physicists sometimes describe as a light-like connection. Rather than thinking of the photon as gradually crossing space second by second, we can picture the photon tracing a thread through space-time that directly connects the moment of its creation with the moment of its arrival. This idea may feel difficult to picture because our everyday experience is built on slower speeds. In our lives, journeys always require time. Walking across a room takes seconds. Traveling between cities takes hours. Crossing oceans takes days. Even the fastest spacecraft humanity has ever launched would require thousands of years to reach the nearest stars. Our intuition is built around the idea that distance and time are always linked, but light reveals that the structure of space-time is deeper than our everyday experience suggests. There exist special paths, those traced by photons, where the usual connection between distance and duration disappears. Along those paths, events that appear enormously separated from our perspective can be joined by a single timeless connection. To see how strange this can become, imagine a photon created in a distant galaxy billions of years ago. That galaxy may lie so far away that the light we observe tonight began its journey before Earth even formed. The photon left its star, crossed the expanding universe, passed countless other galaxies along the way, and eventually arrived here. From our point of view, that journey lasted billions of years. Entire civilizations could rise and fall during such a span of time. Yet along the photon's path through space-time, the geometry still connects the beginning and the end of the journey without any passage of time. The moment of emission and the moment of detection lie along the same thread. This does not mean the photon somehow experiences the entire universe instantly. Relativity does not allow us to assign a normal frame of reference to something moving exactly at the speed of light. But the mathematical structure describing spacetime still reveals something beautiful. The paths taken by light form the skeleton of causality in the universe. They mark the boundary between events that can influence one another and events that cannot. Whenever something happens, a star explodes, a planet forms, a distant galaxy shines, information about that event spreads outward at the speed of light. Those signals travel along the same kind of space-time paths we've been describing. They form expanding spheres of influence, carrying the news of the event across the cosmos. If a signal reaches us, it means the event lies within our region of causal connection. If it never reaches us, the event remains forever beyond our horizon. Light in this sense stitches the universe together. Every photon connects two events in space-time, a star emitting light and an eye receiving that light, a galaxy shining billions of years ago and a telescope detecting its glow tonight. The universe becomes a vast web of events connected by threads of light. And once we begin to think about space-time in this way, another remarkable realization begins to appear. Because the oldest light in the universe comes from a time very close to the beginning of cosmic history. Astronomers can observe faint radiation left over from the early universe, light that has been travelling through space for nearly 14 billion years. This ancient glow fills the entire cosmos. It is sometimes described as the afterglow of the universe's birth, and yet, along the path of those photons, the connection between the beginning of their journey and the moment we detect them today may still lie along a timeless thread, which raises an intriguing question. If the paths of light connect distant moments without the passage of time, what does that say about the structure of the universe itself? Does the universe truly unfold moment by moment the way we experience it? Or could space-time be something more like a vast landscape where events simply exist, connected by these invisible threads of light? To explore that idea, we must take a closer look at some of the oldest light in existence, light that began its journey when the universe itself was still young. As we continue this quiet journey, we arrive at one of the most remarkable discoveries in modern astronomy. All around us, filling every direction of the sky, there exists a faint glow of ancient light. It is not visible to our eyes. We cannot see it shining through the night sky. But with sensitive instruments, scientists have detected this radiation everywhere in the universe. It is called the cosmic microwave background. You can imagine it as the oldest light we can observe, a faint afterglow left behind from the early days of the universe itself. To understand where this light comes from, we need to travel back in time, nearly to the beginning of cosmic history. Today the universe is filled with stars, galaxies, planets, and enormous regions of dark, empty space. But long ago the universe looked very different. If we go back far enough in time, billions of years before the Earth formed, the universe was smaller, hotter, and far denser than it is today. Matter and energy were packed together in a glowing sea of particles. The temperature was so high that atoms could not exist in stable form. Electrons moved freely, constantly scattering light in all directions. The universe at that time was filled with brilliant radiation, but that radiation could not travel far before colliding with particles. Light bounced endlessly from one interaction to another, like a beam trapped inside thick fog. Then something remarkable happened. As the universe expanded, it gradually cooled. After roughly a few 100,000 years of expansion, the temperature dropped enough for electrons and atomic nuclei to combine into stable atoms. When that happened, the fog began to clear. Light was finally able to travel freely through space without constantly colliding with charged particles. In that moment, the universe became transparent. Photons that had previously been scattered again and again were suddenly released to travel across the cosmos. Those photons began a journey that continues even now. They spread outward in every direction, filling the expanding universe with a faint background glow. Over billions of years, the universe continued to grow larger and cooler. As space expanded, the wavelengths of those ancient photons stretched as well. Light that originally glowed with visible brightness gradually shifted into longer wavelengths, becoming microwave radiation by the time it reached us today. That faint microwave glow is what we call the cosmic microwave background. Sensitive radio telescopes can detect it coming from every direction of the sky. No matter where astronomers point their instruments, north, south, toward distant galaxies, or into seemingly empty space, the same ancient radiation appears. It forms a nearly uniform background across the entire universe. This discovery was one of the strongest confirmations that the universe began in a hot, dense state long ago. It provides a snapshot of the cosmos when it was only a few 100,000 years old, an instant in cosmic terms compared with the nearly 14 billion years that have passed since then. When scientists study this radiation carefully, they find tiny variations in temperature across the sky. These variations are incredibly small, differences of only a few millionths of a degree. Yet they reveal subtle patterns that show where matter in the early universe was slightly more concentrated. Over billions of years, gravity amplified those tiny differences. Regions with slightly more matter gradually pulled in surrounding material, eventually forming the galaxies and galaxy clusters we observe today. In this way, the cosmic microwave background acts like a fossil from the universe's infancy. It preserves the earliest patterns that later grew into the vast cosmic structures surrounding us. But beyond its importance for cosmology, this ancient radiation connects beautifully with the ideas we have been exploring tonight. Because every photon in that background glow began its journey billions of years ago. These photons have travelled through the expanding universe almost since the beginning of cosmic time. They crossed immense distances, passing countless galaxies along the way. Some of them are reaching our detectors right now. From our perspective, their journey has lasted nearly 14 billion years. Yet along the path followed by each photon through spacetime, the geometry still connects the beginning and end of that journey without the passage of time. The moment those photons were released into the transparent universe and the moment we detect them today lie along the same kind of light path we have been discussing. A path where time does not accumulate. This means that the faint microwave glow filling the sky is not only ancient light, it is also light whose entire journey may lie along a timeless connection through space-time. The birth of those photons and their arrival in our instruments are joined by threads that stretch across the history of the cosmos. And that realization invites us to think about the Big Bang in a slightly different way. Because if photons from the early universe travel along paths where time does not pass, then the moment of their origin may still be connected to the present in a way that challenges our everyday sense of time. The universe may not simply be a story unfolding second by second. Instead, space-time might be more like a vast structure where events across billions of years remain quietly connected. Light reveals those connections. It carries messages from the early universe into our telescopes and our laboratories, and it reminds us that even the oldest light in existence is still part of the same cosmic fabric that surrounds us today. Let us return to that ancient glow filling the universe. In the previous session, we discovered that the cosmic microwave background is made of photons released when the universe first became transparent. Those photons have been travelling across the expanding cosmos for almost the entire history of the universe. But it is one thing to say that light has travelled for billions of years. It is another thing to pause and imagine what that really means. Picture one of those photons. It begins its journey when the universe is still young. Galaxies have not yet fully formed. Stars are only beginning to appear in scattered regions of space. The cosmos itself is smaller and denser than it is today. In that moment, the fog of charged particles clears and light is finally able to travel freely. A photon is released. It begins moving outward through space at the speed of light, racing across the universe at about 300,000 kilometers every second. At first, the universe around it looks very different from what we see today. Galaxies are still forming. Clouds of gas are collapsing under gravity. The first generations of stars ignite. The photon continues travelling. Millions of years pass, then billions. During this time, the universe itself expands. Space stretches in every direction. Galaxies drift farther apart from one another. Vast cosmic structures slowly emerge. The photon continues its journey through this expanding landscape. It crosses enormous regions of space. It passes galaxies containing hundreds of billions of stars. It travels through dark cosmic voids where almost nothing exists except faint radiation. And eventually, after nearly 14 billion years of cosmic history, the photon arrives here. Perhaps it enters a radio telescope on Earth. Perhaps it is detected by a spacecraft studying the microwave background. Perhaps it contributes to a map of the early universe that astronomers use to study cosmic structure. From our perspective, that photon has been travelling for almost the entire lifetime of the universe. It left its birthplace when the cosmos was only a few 100,000 years old. Now it arrives when the universe is nearly 14 billion years old. But relativity invites us to view this journey from a different angle. Instead of imagining the photon moving step by step through time, we can think of its entire path through space-time as a single connection between two events. The first event is the moment the photon was released when the universe became transparent. The second event is the moment that photon reaches our detector today. Between those two events lies the path taken by light, and along that path the passage of time is zero. This is one of the quiet but profound consequences of relativity. The universe may contain enormous stretches of time between events, when viewed from our everyday perspective, yet those same events can be connected by light paths where time does not accumulate. The photon's journey does not contain moments unfolding one after another. Instead, its beginning and its end lie along a single geometric thread through space-time. This idea can feel strange because our experience of time is so deeply rooted in memory and sequence. We remember yesterday, we anticipate tomorrow, we feel time flowing continuously from one moment to the next. But relativity shows that the structure of space-time is more subtle. Different observers can trace different paths between events. Some of those paths accumulate time. Others, those followed by light, do not. If we imagine the universe as a vast four-dimensional landscape, then photons trace the sharpest possible routes through that landscape. They connect events across enormous cosmic distances without accumulating time along the way. The birth of the photon and its arrival, billions of years later, lie along the same line in space-time. In this sense, the oldest light in the universe still carries a direct connection to its origin. Every photon of the cosmic microwave background links us to a moment when the universe first became transparent. When our instruments detect those photons today, we are not merely observing ancient history. We are touching a thread that stretches all the way back to the early universe. This realization becomes even more fascinating when we think about the expansion of space. As the universe expands, galaxies move farther apart. Distances between cosmic structures increase over billions of years. But the path of a photon adapts naturally to this expansion. The photon continues traveling through the changing geometry of space-time, following the same kind of light path from beginning to end. Along that path, the geometry still connects the moment of emission and the moment of detection. The expansion of space stretches the wavelength of the photon, turning originally energetic radiation into the faint microwave glow we observe today. But the space-time connection between its beginning and end remains intact. It is as if the universe has been quietly delivering a message from its earliest days, carried across billions of years by threads of light. Each photon arriving in our detectors today is part of that message, and each one reminds us that the story of the universe is written not only in matter and galaxies, but also in the geometry of space-time itself. Light carries information across the cosmos. It connects distant events. It links the earliest moments of the universe to the present day. And it does so along paths where the familiar flow of time disappears, which raises an intriguing possibility. If light connects events across billions of years without the passage of time along its path, then our usual idea of a single universal moment, the idea of now, may not exist in the way we imagine. Different observers moving in different ways through space-time may disagree about which events happen at the same time, and that realization leads us toward one of the deepest insights of Einstein's theory of relativity. Up to this point in our journey, we have slowly uncovered several surprising features of the universe. We have seen that time can stretch and slow when objects move very quickly. We have seen that distances can shrink for travelers racing through space. And we have followed the paths of photons, discovering that light connects distant events along threads where time itself does not accumulate. All of these ideas hint at something deeper. They suggest that our everyday understanding of time, especially the idea of a single shared present moment, may not reflect how the universe truly works. In daily life, it feels natural to imagine that the entire universe shares the same now. Right now, you might be sitting in a quiet room, perhaps listening to this story in the evening or the early hours of the morning. It feels as though the present moment exists everywhere at once. The Earth is turning beneath the sky. Cities across the planet are alive with activity. Stars shine quietly above us. And it feels as though all of these things are happening together in the same moment. But relativity quietly challenges this assumption. To see why, imagine a simple scene involving two observers. The first observer stands on the ground, watching a long train rush past at tremendous speed. The second observer sits inside the train itself. Now imagine that two flashes of lightning strike the train, one near the front and one near the back. To the observer standing beside the tracks, the flashes might appear to happen at exactly the same moment. Light from both strikes travels toward the observer, and the two bursts of light reach their eyes at the same time. From their perspective, the lightning strikes occurred simultaneously. But for the observer riding inside the train, the story can look different. Because the train is moving forward, the observer inside is travelling toward the flash at the front of the train and away from the flash at the back. As a result, the light from the front strike reaches the observer before the light from the rear strike. At first glance, this might seem like a simple difference in travel time for the light signals. But relativity tells us something more subtle is happening. When the observer inside the train accounts for their motion and the constant speed of light, the conclusion they reach is surprising. From their perspective, the lightning strike at the front of the train actually occurred earlier than the strike at the back. In other words, two observers moving relative to each. Others can disagree about whether events happened at the same time. The idea that events can be simultaneous for one observer but not for another is known as the relativity of simultaneity. It is one of the central features of Einstein's theory of relativity, and once we accept this idea, our concept of a universal now begins to dissolve. If two observers moving differently through space can disagree about the timing of events, then the universe cannot possess a single global present moment shared by everyone. Instead, each observer carries their own slice of space-time, a particular way of dividing events into past, present, and future. You can imagine space-time as a vast four-dimensional landscape filled with events. Each observer moving through this landscape traces a path. Along that path, they experience moments unfolding one after another. But the way they slice that landscape into moments depends on how they move. Observers travelling at different speeds tilt their slices of space-time in different directions. One observer's present moment may include events that another observer considers part of the past or the future. This idea can feel deeply counterintuitive because our everyday experiences involve very small differences in speed compared with the speed of light. Two people walking down the same street share nearly the same motion through space-time, so their definitions of now almost perfectly agree. But when objects move at extremely high velocities, the differences become more noticeable. Astronauts travelling through space, observers near rapidly moving objects, and light signals travelling between distant regions can reveal how flexible our concept of time really is. Relativity does not say that time is an illusion. We still experience the flow of time in our daily lives. Clocks still measure durations. Events still unfold in sequences. But relativity shows that these sequences are not arranged around a single universal moment. Instead, the structure of space-time contains many possible ways to organize events into past, present, and future. Each observer's motion through space-time determines their own ordering of events. And once we begin to think about time this way, another remarkable possibility begins to emerge. If there is no single universal now, then perhaps the universe does not evolve through time in quite the way we imagine. Instead of events coming into existence moment by moment, the entire history of the universe might exist together within the structure of space-time. Past events, present events, and future events could all be part of the same four-dimensional landscape. Our experience of time would then be similar to moving along a path through that landscape, encountering events one after another as our consciousness travels along its world line. This interpretation is sometimes called the block universe. In the next part of our journey, we will explore this idea more gently, because once we begin to think about space-time as a vast structure containing all events, the role of light becomes even more fascinating. Light does not merely travel through the universe, it weaves together the connections between events across that four-dimensional landscape. For most of human history, the idea of a shared present moment felt almost unavoidable. If two people stood beside each other and looked at the sky, they would both say the same thing. The sun is shining, the clouds are drifting slowly, the wind is moving through the trees. Everything around them appears to belong to the same moment. Even when we think about distant places, cities on the other side of the planet or stars far above us, it feels natural to imagine that the entire universe shares one common now. Somewhere on Earth the morning is beginning, somewhere else the evening is settling in, but all of those events feel as though they belong to the same slice of time, yet relativity gently reshapes this picture. To understand why, let us imagine something simple again. Two astronauts are travelling through space in different directions, each moving at tremendous speed. One heads toward a distant galaxy, while the other travels back toward Earth. Because both astronauts are moving very quickly relative to one another, their clocks tick at slightly different rates. But relativity goes even further than that. It tells us that these astronauts will also disagree about which distant events are happening at the same time. Imagine that somewhere far away, two stars explode in brilliant supernova explosions. From the viewpoint of one astronaut, the two explosions might appear to happen simultaneously, but from the viewpoint of the other astronaut, moving differently through space, one explosion may appear to happen earlier than the other. Neither observer is wrong. Each one is describing the universe according to their own motion through space-time. In other words, simultaneity depends on the observer. This realization changes something fundamental. It means that the universe cannot possess a single global clock ticking everywhere at once. There is no master timeline dividing the entire cosmos into perfectly synchronized moments. Instead, each observer carries their own sense of time with them. Their motion through space determines how they slice the four-dimensional structure of space-time into moments that feel like now. You can imagine space-time as an enormous landscape made not only of locations in space, but also moments in time. Every event, every star explosion, every birth of a galaxy, every moment in human history occupies a specific place within this four-dimensional structure. Observers moving through this landscape trace paths through it. Physicists often describe these paths as world lines, meaning the route an object takes through space-time as time passes. But the way each observer divides space-time into present moments depends on how they move along that path. One observer's present might include events that another observer considers part of the past. Another observer's present might include events that someone else believes have not happened yet. This is not an illusion or a trick of perception. It is a genuine feature of how space-time is structured. In everyday life, we do not notice this effect because our speeds are extremely small compared with the speed of light. Two people walking down a street, or even flying across the planet in an airplane, are moving so slowly relative to the cosmic speed limit that their definitions of now remain almost identical. But when speeds become enormous, approaching the speed of light, the differences become more pronounced. Different observers carve space-time into moments in slightly different ways, and once we accept this idea, something quietly remarkable appears. If there's no universal present moment, then perhaps the universe does not unfold. In time, in the way we often imagine, we often picture the universe as a story being written moment by moment. First comes the past, then comes the present, then the future gradually unfolds. But relativity invites us to imagine another possibility. Instead of the universe being written page by page, the entire story might already exist within the geometry of space-time. All events, past, present, and future may simply occupy different locations within the same four-dimensional structure. Our experience of time would then arise from the way we move through that structure. We would encounter events along our world line one after another, giving the impression that time is flowing. But the larger structure of space-time would already contain the entire history of the cosmos. This idea can feel strange at first. After all, our memories only reach into the past. The future feels open and uncertain. Yet relativity suggests that the division between past and future may depend partly on how we move through space-time. Different observers might disagree about which distant events belong to the present moment, and if the present itself is not universal, then the universe may not evolve through time in quite the way we imagine. Instead, it may exist as a vast geometric structure where events are connected by paths through space-time. Within that structure, light plays a particularly special role. Because light always travels at the cosmic speed limit, it traces the boundaries of how events can influence one another. Light defines the limits of causality, the regions of space-time where signals and information can travel. Photons weave together the connections between distant events, linking them across enormous stretches of space and time. And along those paths of light, something extraordinary happens. The usual passage of time disappears, which means that when a photon connects two events across billions of years, the beginning and the end of that journey lie along a single, timeless thread. That realization brings us closer to an even deeper idea about the nature of reality itself. Because if the universe does not possess a universal present moment, and if light connects distant events without the passage of time along its path, then the structure of space-time may hold all events together in ways that challenge our everyday experience of time. And this is where one of the most intriguing interpretations of relativity begins to emerge, a view sometimes known as the block universe. When we imagine the universe, we often picture space as a vast stage. Stars appear scattered across the sky. Galaxies drift slowly through enormous cosmic distances. Planets orbit their stars while comets trace long curved paths through the darkness. In this familiar picture, space forms the stage on which events unfold, while time flows steadily forward like a river carrying everything along with it. But Einstein's theory of relativity suggests that this picture is incomplete. Instead of thinking about space and time separately, physicists describe the universe as a unified structure called spacetime. Spacetime blends 3 dimensions of space with 1 dimension of time into a single 4-dimensional framework. Within this framework, every event occupies a specific location. An event might be the ignition of a star. It might be the moment a raindrop touches the ground. It might be the instant when a photon from the early universe arrives at a telescope on Earth. Each of these moments can be described by 4 coordinates, 3 describing where the event happens in space, and 1 describing when it occurs. Together, these coordinates place the event within the structure of space-time. To visualize this idea, imagine a vast landscape. Not a landscape made only of hills and valleys, but one that also contains moments in time. Every event in the universe is like a point somewhere within this enormous terrain. Some points represent the formation of galaxies billions of years ago. Others represent moments that will occur far in the future. Still others represent the quiet present moment in which you are listening to this story. In this picture, the universe becomes a kind of cosmic map, containing every event that has ever happened or will ever happen. Objects moving through the universe trace paths across this map. A star traces a path as it moves through space and continues to exist from one moment to the next. A planet traces its own path as it orbits its star year after year. Even you trace a path through space-time as you move through your life. Physicists often call these paths world lines. A world line is simply the route an object follows through space-time as time passes. If you could draw your entire life as a path through this four-dimensional landscape, it would begin at the moment of your birth and continue forward through every moment you experience. Your world line would twist gently as you travel across Earth's surface. It would curve as our planet moves around the sun, and together with billions of other world lines from people, animals, stars and galaxies, it would form a vast tapestry of paths woven through space-time. Within this structure, light traces very special paths. Unlike objects with mass, photons always move at the cosmic speed limit. They cannot slow down or speed up. Because of this, the paths taken by light mark the boundaries of how events can influence one another. If one event sends out a flash of light, that flash spreads outward through space-time carrying information about the event. Any other event that lies along the path of that light can be affected by it. For example, when a distant star explodes as a supernova, light from that explosion begins travelling across the universe. Eventually, that light may reach a telescope on Earth, allowing astronomers to observe the event. The explosion and the observation become connected by a thread of light through space-time. This connection forms part of the causal structure of the universe. Causality simply means that one event can influence another. Light defines the maximum speed at which that influence can travel. No signal, no particle, and no information can move faster than light. Because of this limit, the structure of space-time divides events into different regions. Some events can influence one another because light has time to travel between them. Other events are so distant that no signal travelling at the speed of light could ever connect them. In this way, space-time contains not only the locations of events, but also the relationships between them. Events connected by light can affect each other. Events outside those connections remain forever separate. Within this geometric picture, the universe becomes less like a flowing river and more like a vast landscape filled with paths and connections. Objects follow world lines through this landscape. Light weaves threads linking distant events, and the geometry of space-time determines which events can influence others. This perspective begins to shift how we think about time itself. Instead of imagining time as something that moves, we can imagine ourselves moving through space-time. Just as a traveller walking through a forest encounters trees and streams along the path, we encounter events along our world line. Moments appear to pass because our consciousness experiences events one after another along this path. But the broader structure of space-time may already contain all of those events together. The formation of distant galaxies, the birth of our sun, the quiet moment you are living now. All of these may simply occupy different locations within the same four-dimensional landscape. And within that landscape, the paths of light form the delicate threads tying distant moments together. These threads stretch across billions of years of cosmic history, linking the earliest light of the universe with the present day. As we continue our journey, this geometric view of space-time will lead us toward one of the most intriguing interpretations of relativity, an interpretation that suggests the universe might not be evolving moment by moment at all. Instead, the entire history of the cosmos may exist together as a single structure within space-time, a view often described as the block universe. Once we begin thinking about space-time as a landscape filled with events, a quiet but profound idea begins to emerge. If every event occupies a position within this four-dimensional structure, then perhaps the universe is not unfolding moment by moment the way we usually imagine. Instead, the entire history of the cosmos might already exist within the geometry of space-time itself. Physicists sometimes refer to this idea as the block universe. The name may sound mysterious at first, but the basic picture is surprisingly simple. Imagine a large book. every page of the book already exists at the same time. The first page, the middle chapters, and the final page are all part of the same physical object. Yet when you read the book, you experience the story gradually. You read one page, then the next, and then the next. From your perspective, the story seems to unfold over time. But from another perspective, the perspective of the book itself, the entire story already exists. The block universe suggests something similar about space-time. Instead of the universe being written moment by moment like ink appearing on blank paper, the entire story of the universe may already exist within the structure of space-time. The birth of stars billions of years ago, the formation of galaxies, the rise of life on Earth, and even moments far in the future. All of these events could simply occupy different regions within the same four-dimensional structure. In this view, time does not flow in the universe itself. Rather, our experience of time arises because we move along our own world lines through space-time. As we travel along that path, we encounter events one after another. The events behind us form what we call the past. The events ahead of us form what we call the future. And the event we are experiencing right now becomes the present moment. But the structure of space-time itself may contain all of those events together. From this perspective, the difference between past, present, and future is not a property of the universe as a whole. Instead, it reflects how individual observers move through space-time. To understand this more clearly, imagine once again that enormous space-time landscape we discussed earlier. Within that landscape lie countless points representing events. Some correspond to moments that happened billions of years ago. Others correspond to events that will occur long after our own time. But all of these points exist within the same structure. Our lives trace paths through this landscape. We move steadily along our world lines, encountering events sequentially. From our personal perspective, time appears to flow, but the landscape itself may remain unchanged. This interpretation does not mean that the future is predetermined in a rigid sense. Rather, it suggests that the structure of space-time contains all events in a geometric relationship. Just as every location on a map exists simultaneously, every event in space-time may exist within the same four-dimensional framework. Our movement through space-time gives rise to the experience of change. The stars rise and set, seasons pass, years slip by. Yet these experiences might reflect our journey through the space-time landscape rather than a universal clock moving forward. The block universe idea also fits naturally with the relativity of simultaneity that we explored earlier. Because different observers moving through space-time can disagree about which events happen at the same time, the universe cannot possess a single shared present moment. Instead, each observer defines their own slice of space-time as the present. If we imagine slicing through that space-time landscape at different angles, different observers would draw different now surfaces across the same structure. Each slice would contain events that appear simultaneous from that observer's point of view. But other observers moving differently would carve the landscape in slightly different ways. The space-time structure itself remains the same, only the observer's perspective changes. This geometric view of the universe may seem unusual at first. After all, our daily experience of time feels vivid and undeniable. Moments pass, memories accumulate, the future feels open and unwritten. Yet physics often reveals that the structure of reality is not always identical to our everyday intuition. Just as Earth once seemed flat before we understood its true shape, time may feel like a flowing river, even if the deeper structure of space-time resembles a vast landscape. And within that landscape, light plays an especially remarkable role. Photons trace the fastest possible paths through space-time. They connect distant events along threads where the usual passage of time disappears. This means that when a photon leaves a distant galaxy and eventually reaches our eyes, The emission and the detection lie along a single timeless connection. For us, billions of years may pass between those events, but along the path of light, those moments remain linked without the accumulation of time. In the block universe picture, light becomes one of the threads stitching together the fabric of space-time. Every beam of light connects events across vast distances. Every photon traces a path linking moments in the cosmic story, and when we observe light that has travelled across billions of years, we are glimpsing those connections within the space-time structure. Which leads us toward one final and fascinating question. If photons experience no passage of time along their paths, then what does the beginning of the universe look like from the perspective of light itself? Could the earliest moments of the cosmos still be connected directly to the present through those timeless threads? And if so, might the birth of the universe be closer than we imagine? Let us return, one more time, to that ancient moment when the universe first became transparent. For hundreds of thousands of years after the Big Bang, the universe was filled with a hot, glowing fog of charged particles. Light could not travel freely because photons were constantly colliding with electrons and protons. But as the universe expanded and cooled, something remarkable happened. Electrons and protons combined to form neutral atoms. Once this occurred, the fog cleared. Light was finally able to travel long distances without being scattered. In that moment, the universe filled with radiation moving freely in every direction. Those photons began journeys that would last, from our perspective, almost the entire lifetime of the universe. Some of them are still travelling today. A few of them eventually reach Earth, where sensitive instruments detect their faint microwave glow. This ancient radiation is what we call the cosmic microwave background. When astronomers study this light, they're observing photons that have travelled across the expanding universe for nearly 14 billion years. It is one of the oldest signals we can observe. Yet relativity invites us to look at this journey in a different way. From our perspective as observers made of matter, those photons have travelled an immense distance across cosmic time. But along the path taken by light itself, the situation is very different. For objects with mass, time flows along the path they trace through space-time. Clocks tick, processes unfold, moments accumulate one after another, but light follows a special type of path through space-time, where the passage of time along that path becomes zero. In other words, a photon, travelling through empty space, does not experience a sequence of moments along its journey. The emission of the photon and its eventual absorption remain connected along a single thread through space-time. For us, those events may be separated by billions of years, but along the photon's path, the interval of experienced time vanishes. The beginning and the end of the journey lie along the same timeless connection. This idea does not mean that photons possess consciousness or awareness. Light does not experience time in the way living beings do. Rather, it means that the geometry of space-time connects the emission and detection of the photon without the accumulation of time along that path. The photon's trajectory simply links those two events directly. And this leads to a fascinating implication. Consider one of the photons released when the universe first became transparent, nearly 14 billion years ago. That photon begins its journey in the young universe. It travels outward through expanding space. It crosses vast cosmic distances. Eventually it arrives at a telescope on Earth. From our perspective, the journey took billions of years. But the path traced by the photon through space-time connects those two events without the passage of time along the path itself. The moment the photon was released and the moment it was detected lie along the same light path. They are joined by a thread that contains no elapsed time. In a sense, the earliest light in the universe remains directly connected to the present. Every time we detect a photon from the cosmic microwave background, we are touching a signal that has travelled almost the entire age of the cosmos. Yet along the photon's own path, those two events remain joined in a timeless way. The emission of the photon and its detection lie along the same geometric thread within space-time. It is as though the birth of that photon and the moment of observation are connected by a line that bypasses the usual accumulation of time. From this perspective, the ancient light of the universe forms a bridge linking the earliest visible moments of cosmic history with the present day. Every photon arriving from deep space carries with it a connection to a distant moment in the past. And because light travels at the cosmic speed limit, those connections define the structure of causality across the universe. Light determines which events can influence which others. Signals cannot move faster than light. Information cannot outrun it. In this way, photons weave together the causal structure of the cosmos. They carry information across space. They link distant events. They define the boundaries of what can affect what. And along their paths, time itself does not accumulate. This does not mean that the Big Bang is literally happening right now in the everyday sense. But it does suggest that the earliest observable moments of the universe remain connected to the present through the geometry of space-time. Light forms the threads tying those distant moments together. When we observe ancient photons arriving from the edge of the observable universe, we are witnessing connections that stretch across billions of years of cosmic history. And yet along the paths traced by those photons, the emission and the detection remain joined by a thread that contains no passage of time. This extraordinary feature of relativity brings us very close to the central question of our exploration. If light connects distant events without the accumulation of time along its path, then perhaps the beginning of the universe and the present moment are not as separate as they appear. Perhaps they occupy different locations within the same four-dimensional structure of space-time, a structure in which light quietly weaves together the earliest moments of the cosmos with the quiet present in which we now find ourselves. At this point in our journey, we have arrived at a rather unusual crossroads. On one hand, our daily experience tells us that time flows, moments pass, memories accumulate, the future slowly approaches while the past slips quietly behind us. Everything about our lives seems to confirm that time is moving forward like a river carrying us along. And yet the physics we have explored paints a more subtle picture. Relativity suggests that space-time may already contain the entire history of the universe within its structure. Past events, present events, and future events could all exist as different locations within the same four-dimensional landscape. If that is true, then an interesting question appears. If the universe itself may not be flowing through time, why does time feel so vividly real to us? Why do we experience the steady passage of moments? One possible answer lies in the difference between the structure of the universe and the way observers move within it. Earlier, we introduced the idea that every object traces a path through space-time. These paths represent how objects move through both space and time. Physicists often call these paths world lines. Your world line began at the moment of your birth. Since then, it has continued forward through every moment you've experienced. Right now, as you sit or lie quietly listening to this story, your world line continues gently forward through space-time. You're moving through time at what we might call the ordinary human pace. Clocks tick, hearts beat, thoughts arise and fade. Your experience of the present moment moves steadily forward along this path. From your perspective, time appears to flow. But imagine stepping back and looking at the entire space-time landscape from a wider view. From that perspective, your world line would appear as a long curve stretching from the moment of your birth into the future. Every event along that path, every conversation, every quiet evening, every moment of wonder would already exist as points along that line, you would not see time flowing. Instead, you would see a path through the space-time structure. Your experience of the passage of time would arise because your consciousness encounters events along that path one after another. It is similar to walking along a trail through a forest. The entire trail exists whether or not you have reached the end of it. But as you walk, you encounter each bend in the path one by one. To the traveller, the landscape appears gradually. Yet the landscape itself does not unfold. It is simply there. Some physicists and philosophers believe our experience of time may work in a similar way. The universe might exist as a complete space-time structure, while observers move along their world lines encountering events sequentially. The sensation that time is flowing would then arise from the way our minds process these events. Memory plays an important role here. We remember events that lie earlier along our world line. We do not yet remember events that lie further along the path because of this asymmetry. The future feels open while the past feels fixed. But in the space-time picture, both regions may simply exist at different positions within the same structure. Another important element is causality. Events along our world line influence one another. The choices we make today shape the events we encounter tomorrow. Light signals carry information between events, ensuring that causes precede their effects. These causal connections create the orderly sequence we experience as the flow of time. But the geometry of space-time itself may simply contain all of these connections at once. Within that structure, light again plays a crucial role. Because photons travel at the cosmic speed limit, they trace the boundaries of how events influence each other. Every flash of light, every radio signal, every beam of starlight carries information along these causal pathways. And along those pathways, the passage of time behaves differently than it does for objects with mass. For photons, the geometry of space-time links the beginning and end of the journey without the accumulation of time along the path. For us, the same journey may span billions of years. This difference highlights something profound. Time may not be a single universal experience shared by all things. Instead, different kinds of paths through space-time accumulate time differently. Objects with mass experience time along their journeys. Light does not, and consciousness, whatever its deeper nature may be, moves along the world lines of living beings, encountering events in sequence. From our perspective inside that journey, time feels vivid and real. Moments appear, unfold, and fade. But from the wider perspective of space-time, those moments may simply occupy different locations within a timeless structure. The universe might not be flowing forward at all. Instead, it could resemble an enormous cosmic landscape where every event already has its place. Within that landscape, stars form and galaxies drift. Civilizations rise and fall. And along countless world lines, conscious observers move through their personal histories. Each observer experiences time in their own way. Each path through space-time reveals events in a particular sequence. And along the threads traced by light, distant moments remain connected without the passage of time. Which brings us to one final reflection. If photons connect events across billions of years without experiencing time along their paths, and if observers experience time because of how they move through space-time, then the universe itself may be far quieter and more timeless than our everyday experience suggests. As our exploration gently approaches its final moments, it may be helpful to pause and step back for a moment. Throughout this journey, we have followed a simple question that slowly unfolded into something much deeper. Why might light, in a sense, be older than the universe? The answer did not lie in a single equation or a single experiment. Instead, it emerged gradually as we explored the nature of space, time, and the strange behaviour of light itself. We began with something familiar: sunlight reaching your skin, a beam of light crossing the room, a distant star shining quietly in the night sky. Light feels ordinary because it surrounds us everywhere. And yet the moment we begin to examine it closely, light reveals some of the most surprising truths about the universe. One of those truths is that the speed of light is not just another speed in nature. It is the ultimate speed limit of the cosmos. Nothing that carries information or influence can travel faster than light. This cosmic speed limit quietly shapes the structure of reality itself. Because light travels at this special speed, space and time cannot remain independent. Instead, they become woven together into the fabric we call spacetime. Movement through space changes the passage of time. Clocks slow when objects move, extremely fast. Distances shrink along the direction of motion. These effects are not illusions. They are genuine features of how the universe is built. As objects move closer to the speed of light, time slows more and more dramatically, and at the speed of light itself, something remarkable occurs. Along the path followed by light, the accumulation of time disappears. The beginning and the end of the photon's journey remain connected by a thread through space-time, where the usual passage of time does not occur. For us, light from distant galaxies may travel across billions of years before reaching Earth. But the geometry of space-time links the emission and the arrival of that light along a path that does not accumulate time. This insight leads us to one of the most beautiful realizations in modern physics. Light connects distant moments in the universe. Every photon arriving from deep space forms a bridge between two events. One event may be the explosion of a distant star billions of years ago. The other event may be the moment a telescope detects the faint glow of that explosion tonight. These two events lie at opposite ends of a path traced by light through space-time, and along that path time does not accumulate. In a sense, the ancient star and the present moment remain linked by a timeless connection. When astronomers study light from distant galaxies, they are not merely observing objects far away. They are receiving signals that have travelled across enormous stretches of cosmic history. Every beam of starlight carries a story. Some of those stories began before our planet even formed. Others began long before the first life appeared on Earth. And yet those photons are arriving here now, quietly linking those distant events to our present moment. The same is true of the oldest light we can observe, the faint microwave glow that fills the sky in every direction. Those photons began their journey when the universe was still very young. At that time, the cosmos had cooled enough for light to travel freely through space. Nearly 14 billion years have passed since then. Galaxies have formed, stars have lived and died, planets have emerged around distant suns. Life has arisen on at least one small world, and throughout that vast history, those ancient photons have continued travelling through the expanding universe. Eventually, a small number of them reach the detectors of modern telescopes. To us, their journey spans almost the entire age of the universe. But along the path traced by the photon through space-time, the emission and the detection remain joined along a single geometric thread. The beginning of the journey and the end of the journey lie along a path that does not accumulate time. This realization does not mean that time itself is unreal. For beings like us, made of matter, moving far below the speed of light, time remains a fundamental part of experience. Our lives unfold moment by moment. Memories accumulate behind us. The future stretches ahead. Yet the deeper structure of the universe may be far quieter than the flowing river of time we perceive. Space-time may simply contain the entire cosmic story within its geometry. Every event, past, present, and future, may occupy its place within that four-dimensional landscape. Within this structure, light weaves together the connections between distant events. Photons travel along the boundaries of causality, linking moments across space and time. They carry information across the cosmos. They connect ancient stars to modern telescopes. They connect the earliest visible moments of the universe to the quiet present in which we now find ourselves. And so, the question that began our journey slowly finds its answer. Light may appear older than the universe, not because it existed before the cosmos began, but because the geometry of space-time allows light to connect distant moments without the accumulation of time along its path. The beginning and the end of a photon's journey remain joined along a timeless thread. And when we look up at the night sky and see starlight shining across the darkness, we are witnessing those threads. Connections stretching across billions of years, quiet bridges linking distant moments in the history of the universe. A universe that may be far more still and far more timeless than it first appears.